guys, this video is regarding the switching electrical control scheme for thermistors. See, in a power electronics converter is useful when its output voltage is controllable. Now there are different schemes available for controlling of the output of the different converters, likely time ratio control for DC chopper, PWM control for inverter, etc. For phase control rectifier, the technique is switching angle control or control of switching angle. Now in this video basically we are going to cover these four schemes. One is the cosine wave crossing control, second is the ramp comparator control, and third is digital firing scheme, and fourth one is equidistant pulse firing scheme. Now the first scheme, which is basically a cosine wave crossing control, that we are going to discuss first, is obtained from the input supply through an integrator, because integration of a sine wave is your cosine wave. Now if you see the basic building block diagram of this scheme, circuit arrangement, this is the basic block diagram. In this case, your cosine wave is compared against a DC reference signal and the corresponding trigger pulse is obtained. These are compared with the help of a comparator. For in the case of the first comparator, your V2, which is the cosine wave, is compared with the reference signal EC. So you can see whenever EC is greater than V2, your pulse is generated. While in the comparator 2, whenever V2 is greater than of a minus of minus EC, your V4 is generated. You can verify with the help of this one. So the first one was when you see again, please. First one, comparator 1, EC greater than V2. So EC, whenever EC is greater than this, so if you see here EC is greater than V2, so your pulse is generated. Now in the second case, if you see the second case, your V2 is greater than of minus of EC. So V2 is greater than of minus of EC. V2 is greater than of minus of EC. So here your V2 is greater than of minus of EC. So pulse is generated. So in this way, these pulses V4 and V3 is generated. See, the basic principle is similar to that of a dual converter, in which output voltage ratio is equal to the cosine of the firing angle. And based on this, rectifier can be thought of as an amplifier with linear transfer characteristics. I will show you how it is a linear transfer characteristics. So here is the waveform I have shown you. See again, please, back to the circuit. If you here, the input supply is synchronized and step down through a synchronizing transformer to obtain V1. Then it is fed to the integrator to obtain the cosine signal V2. The cosine wave is compared against a control voltage which is limited to plus minus of EC. V3 is the output of the comparator 1, which is obtained when EC is higher than V2. Similarly, V4 is obtained from comparator 2. The signal V3 and V4 make the clock pulse generator to produce output pulses, which in turn set the respective flip-flops, JK flip-flops. The output Vi and Vj of the flip-flop can be used to trigger SCR in a single phase converter. In practice, flip-flop are ended with high frequency carrier, approximately 3 to 5 kHz, to obtain the pulse train, which is shown here. So again, back to the waveforms. So you can say whenever we obtain V3 and we have a corresponding pulse from the clock generator V5, and this is Vi and Vj, which is the output of the JK flip-flop, and this is synchronized with the help of a this is actually basically ended with a high frequency carrier wave, which is approximately 3 to 5 kHz, to obtain a pulse train. You can do that. Now what I've said you it has a linear transfer characteristics. I'll show you how. So firing angle is governed by the intersection of the cosine wave and the control angle. So V2 V cos alpha is equal to EC. So alpha is cos inverse E by VC V. So now for the single phase full bridge rectifier, we know that output voltage is 2 Vm by pi cos alpha. So we can replace alpha with the cos inverse E by 2M. So we get that your output voltage is proportional to the control voltage. So it is directly related. That's why I've said that it has a linear transfer characteristics. This basically helps to improve the closed loop response of the converter. Some remarks. This scheme is sensitive to the line supply variation. For three-phase converter, adjustment should be made to equalize all the line voltage. Otherwise, firing angles will be unequal. But this scheme, the advantage you can say, it has a self-regulating property because any change in the input voltage will lead to corresponding change in the cosine wave, leading to the mean DC voltage being constant. See, the size of the control scheme circuit increases if you increase the number of phases or even the number of phases per pulses increases, because firing pulse is produced individually for each thyristor. You can overcome this by using cosine time multiplexing instead of using individual timing control. Cosine control scheme also applies to the dual and cyclo converter. So here is the basic circuit. If you want to reduce the size by using the multiplexing instead of using a individual timing control. 6 cosine wave are compared using a single comparator. So here is a basic single converter. These waves are passed through a ring counter which get reset after a count of 6. The output of a ring counter goes through decoding and pulse isolation, amplification and high frequency modulation stages before they are fed to the gate of 6 thyristors. Number of components required are reduced, but it still suffers from the drawback of unequal firing angles due to supply and frequency variations. Now we will discuss the next approach, which is basically your ramp comparator approach. So here is a basic block diagram for the ramp comparator, and these are the waveforms. In this case also, line voltage is obtained by using a synchronizing transformer. The signal passes through a zero crossing detector stage where sine wave is converted into a square wave Z or your Z. Sine wave is converted into the square wave. Okay. At the zero crossing of the synchronization signal, a small pulse Vt is produced using monostables. So small pulse is generated, which is basically a clock using the monostables. These pulses are used to generate a ramp voltage through the ramp generator and reset at the end of half period. Thus, the ramp generator is basically an integrator with a fixed DC voltage at the input and a discharge circuit operated by a pulse signal Vt. The ramp voltage is then VRAB here is compared with the control voltage, DC control voltage. So using this logic, we basically get Z6 and Z3. Here is the Z6 and Z3. The ramp voltage is compared with the DC voltage, which is basically the control voltage. At the rising edge of each of these two pulses, small clock pulses are produced using monostables. That is, your clock pulse is generated. Corresponding clock pulses are generated. Each pulse set a flip-flop. These flip-flop are cleared by 2 clock pulses, clock bar, obtained from another channel using appropriate line voltage. Beside the clock pulse, clock bar are used to produce gate pulse for another pair of thyristors. pulses G6 and G3 are produced considering the synchronizing line voltage VAB. Flip-flop producing the pulses G6 and G3 are cleared by another channel where the line voltage VBC, which is lagging behind the voltage VAB by 120 degree. Pulses G6 and G3 are of 120 degree with width each and therefore satisfy the gating requirement. These are produced at the firing angle alpha with reference to voltage VAB and VBA. The long pulses G6 and G3 go through pulse isolation, amplification and high frequency modulation before they are fed to the gate of thyristor T6 and T3. Two similar channels are used considering the line voltage VBC and VCA. The former channel resets the pulses G6 and G3 beside producing pulses G2 and G5 to thyristor T2 and T5, while the later channel resets the pulses G2 and G5 to thyristor T2 and T5. The later channel resets the pulses G2 and G5 beside producing pulses G4 and G1 to thyristor T4 and T1. Now from these waveforms, delay angle alpha can be obtained by when your control voltage become equal to the ramp voltage. So alpha is basically your Vc by Vm into pi equal to K1 into Vc, where Vm is the peak of the ramp voltage. So alpha by pi is basically your control voltage divided by peak of the ramp voltage. Now this output voltage of a bridge converter is 1.35 cos alpha, line to line voltage here we are considering. So alpha is K1 into Vc. Here we are not getting the linear function, we don't have a linear transfer characteristics as in the case of the cosine wave firing scheme. Although your firing angle varies linearly with the control voltage. Also any noise voltage riding on the ramp control or control voltage cause erratic firing. It is quite sensitive to variation in the component value, especially in the ramp generation. Advantage of this method is that it is not sensitive to line voltage fluctuation. Now the next scheme is equidistant pulse firing scheme. In the schemes discussed so far, equidistance of pulses has not been ensured when the line voltage are not 120 degree apart. Also, changes in line frequencies cause appreciable error in the firing angle. The steady state distance between successive firing should be maintained constant in order to avoid undesirable harmonic frequency in the AC source current. Basically, in the equidistance pulse firing scheme, a single pulse train is generated whose phase can be shifted by control voltage Vc. A ring counter with a coding circuit is used to steer the train of pulses in 6 different paths through pulse amplifier and isolation stages. The block enclosed here by the dotted line is basically the PLL, phase lock loop. It consists of a highly stable and linear voltage controlled oscillator VCO, phase comparator, a low pass filter and an amplifier. The PLL contains the output frequency of a VCO at exactly 6n times the main frequency. In the event that main frequency FM changes, then the output frequency of VCO also changes. The frequency FC tracks the main frequency FM. The output frequency of the VCO F0 is divided by 6n to obtain FC, which is compared with and maintained at the same frequency as FM. There may exist a phase difference between FM and FC, but this should be as small as possible in order to minimize error in the firing angle. The maximum error that may be introduced in the equidistant spacing of the 6 consecutive pulses can be 360 degree divided by n, where n is the frequency multiplying factor. So if n is 600, the maximum error in equidistant spacing is 0.6 degree. 360 by 600, which is basically 1 by 360 degree by 600, so 36 by 60, so it is 0.6. The phase control of the pulse train is obtained by comparing the synchronizing supply voltage with the control voltage in a comparator circuit. The phase control of the pulse train is obtained by comparing the synchronizing supply voltage with the control voltage in a comparator circuit. The comparator resets the divided by n counter. At the same time, a small clock pulse is produced at the output of the comparator using a monostable circuit. The pulse resets the ring counter at the count of 6. The output of a ring counter is steered through appropriate blocks to the gates of thyristor. Now the main disadvantage of this scheme is that it requires a minimum delay of at least 1 period to effect any correction in the firing angle. In the scheme discussed earlier, the minimum delay is only 1/6 of a period. Now the next scheme is digital firing scheme. So here is the block diagram and with the relevant waveform. The digital PLL is used to multiply the main frequency by 6 times of twice of with the power of n plus 1, consisting of a basically a divided by 2 n plus 1 counter and a divided by 6 ring counter. The ring counter generates the necessary 3-phase synchronizing waveform which are spaced at 60 degree. Also VCO output is divided by 6. VCO output is divided by 6 ring counter R2. VCO output is divided by 6 ring counter R2 to generate a frequency of 2n plus 1f. This is used to clock 3 sets of n bit down counter 1, 2, 3. The preset enable PE. Points of this down counter is made high at the zero crossing of VAB, VBC and VCA. These zero crossing are obtained by differentiating and adding the appropriate synchronizing waveform obtained from the ring counter R1. The digital control input is used to adjust the firing angle. The carry output of the down counter see carry out, give out pulses after the counting is completed. This information along with the synchronizing waveform is fed to generate phase delayed 180 degree wide pulse at the output of a D-flip flop. These outputs are properly gated to obtain the necessary 180 degree wide pulses. The response time of this scheme in the worst case is 1/6 of the time period, as each down counter is loaded independently by appropriate synchronizing waveform. The resolution of the firing angle is 180 degree divided by 2 with the power of n. An accurate and precise firing delay control is possible. The circuit is insensitive to waveform distortion and transients. The correction of the firing angle takes place within 1/6 of the time period. Okay, this is all for the switching and control.
Bye bye, goodbye. Bye 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 bye, goodbye. I can clap my hands, I can stamp my feet,